Hello, this is the video training for the diode and transistor experiment. The first thing that I wanted to show you is that I want your breadboard to have all the blue lines and the red lines connected to each other. Because in the next few experiments you will have so many devices that will have to be connected all over the breadboard. You don't want to create multiple connections to ground and power. So by connecting them together, you have only one single connection from the power supply to the board, and then whenever I use a blue line, that's ground. Whenever I use a red line, that's power. It doesn't matter which one it is in the circuit. So that's important for you, and you better make it happen before the experiment 5 and 6. That's a must, otherwise you lose points. It's important. The second thing is about the transistors and diodes, and the first part of the diode experiment, of the transistor and diode experiment, is about figuring out that the current flows only in one direction as far as the diode is concerned. As you see, this device, this black cylinder, has a white silver ring. That silver ring, silver ring, and that silver ring happens to be the cathode of the diode. This side is the anode, and this side is the cathode. So when you connect it such that the potential at the anode is higher than the cathode by about 0.6, 0.7 volts, the current will flow in the circuit. Right? Obviously, standard-wise, from anode to cathode to the resistor back to the negative of the power supply, right? Because that's the blue line. So in this case, I'm going to show through the current value that when I connect the circuit using a general purpose diode, because you have other types of diodes in your kit, but you will use them in the next lab in 291. So you will see that if connected this way, the current will flow. If I reverse the diode, right, where the cathode is going to be connected to the positive of the power supply, you will see that no current will flow. So it acts kind of a switch. The only difference between an ideal switch and a diode is the fact that this diode is not a short circuit when the current flows. It is kind of an open circuit because no current will flow in the reverse direction, but in the other direction, it is not exactly 0 volts, so I cannot consider it to be a switch, which means when closed, it will have 0 ohm resistance. But it's close enough to be thought of as an electronic switch. And when we measure the voltage, we'll find out that for general purpose diodes, silicon-based, it's about 0.7 volts or so. For most of them, not constant because it varies with the amount of current that flows, but more or less 0.7 as the value that we use as if it were constant. So right now it's already connected, the power is on, and so as you see through the current, I inserted the ammeter in series. As you see here, the current flows into the red connector of the ammeter, goes to the ammeter, back to the black lead, which goes into the resistor, and back to the negative of the power supply. So when you look at the value of the ammeter, you see 19.4 milliamps or so. And of course, in your head, as I said before, you always try to have estimates of what the value should have been, either calculated or estimated. As I said before, I have a 5 volt from the voltage source, right? I provide. You work with 5 volts in all these parts. So with 5 volts, and assuming there is a 0.7 volt drop across the diode, that means 4.3 across the resistor. This resistor, I believe, is 220 ohms, and therefore 4.3 divided by 220, so it's about 19 to 20 milliamps. And so the value seems to be correct. And of course, if I measure the voltage from here to here, you will see that it's about 0.7, 0.72 or so. And this is as far as the diode in this direction. So to show that in the reverse direction it acts like an open switch, I could have reversed the leads for the power, but I don't want to do that because I already have other circuits from this experiment connected to it. So what I'm going to do, I'm going to reverse the diode itself. So now I connect the cathode to the positive of the power supply. And so now the cathode will have a higher potential than the anode. And theoretically, when you look at the current flow, it's about 0. As you see on the ammeter, you have 0 milliamp, right? And therefore, we know that the diode is acting as an open circuit right now. Another part of the experiment, of course, you're supposed to record these current values for when it is on, when we say it is on, right, in the other direction, and here it is off like an open switch, right? So in this case, I remove this, I insert instead an LED. LED, it's a light emitting diode, which means it is a diode, right? The only difference is that when the current flows, it leads to a diode being on, turned on, or being lit. Now, the way to connect the LED, similarly to the general purpose diode, where the silver ring is the cathode, in this case, the short wire, that's the cathode. And so to turn on, I need the anode connected to the power supply, and the cathode will be used to complete the circuit. And as you see here, because the diode is such, the anode has a higher potential than the cathode, then the current will flow, and if the current flows, that means the LED will turn on. The only difference, big difference between the general purpose diode and the regular LED, you will see that the voltage is not 0.7 volt, but it could be 1.1, it could be, in this case, I believe it's 2.2 for this specific diodes, right? And so that means the rest of the voltage will be across the resistor, and this resistor really is used to limit the current that flows as not to break these devices down. And so we use them for current limitation, right? To limit the current that flows in the circuit to keep these devices safe. So this is the diode section of the experiment. The second part uses a transistor, which of course has been covered in the lecture. And as far as the transistor is concerned, this is a BJT 2N3904. So that's one of the general purpose transistors. And as you see, the flat side, when it's facing you, the pins are such that to the right is the collector, the middle one is the base, and the left one is the emitter. Now, if you look at the circuit will be such that the emitter is connected to ground, and this is what I did. The left one, I connected it to the blue row, that's the ground. And we feed the signal into the base through a protective resistor. Now, for the light bulbs that you have to have enough current to turn it on, and so that you can control also the brightness, even though the manual says multiple kilo ohms, I'm using a 220 ohms, and if low enough, that means the current can be high enough, and the light bulb therefore will light in a way that it is visible, and also you can see the variation in brightness later. But that resistor is definitely a necessity, because without it, the current will be excessive, because the voltage between the base and the emitter, since the emitter is connected to ground, if it exceeds 0.7 to 0.9 volts, that transistor is going to fry. So obviously, to limit the current and to limit therefore the voltage through across the base emitter, this is why we use this resistor into the path of the base. And so this resistor will limit the current in such a way that the base emitter will not exceed 0.7 volt approximately. And the rest, of course, will be across the resistor. But most importantly, that means we decide what the current here is. Now, this device, as you had seen in the lecture, is a current amplifier, which means when we look at the collector current, we're going to see that the collector current is many times the base current. And that's, of course, the basis for current amplification, right? So this device allows the current to be amplified. And so a current that through the base would not even light up this light bulb, through the collector, because it's many times higher, it could be 10 times, 20 times, 50 times. You're going to do measurements. You're going to measure the current through the base, right, by breaking this connection and showing and showing through the ammeter what the current level is. The same thing here, you can break this connection from the collector to the light bulb. So when you remove the wire, you can put the ammeter between the transistor and the wire, and you will see that the current will be many times the current at the base. Of course, your work was to connect the resistor using a switch, but you can use this wire as a switch. So you see here, when I connect it to power, it's as if I have a switch that I turned on, right? See here? So by removing it, it's like I open the switch, and by putting it down, it's like I close the switch. So it's not like you need a switch, you don't need a switch. Just use a wire that goes to the resistor to the base. And so that wire, when connected to, when it's not connected, there'll be no power, no current, because the transistor is current driven. And when I put it into the power line, it draws current IB, which then amplified becomes a current IC, which is high enough to show that the current is high enough for the light bulb to turn on, bright enough also. Now, theoretically, there should have been another portion with the potentiometer. Now, if you look at the potentiometer, that's a device with 3 terminals, but it's 2 resistors. As you have seen in class, there are it's not 2 resistors, it's 1 resistor with a slider that allows R1 and R2 to change values, but the R1 plus R2 is always the sum and equal to a constant, like in this case with the code 103, that means 10 times 10 to the power 3, which means this is a 10 kilo ohm potentiometer. So from the outside terminal, those are the outside terminal, this is where the slider is. From the outside terminal, that's 10 kilo ohms. And in between, it varies, depending on how close it is to this one or to this one. And we use a screwdriver to change the value. If I put it back, now if the left one is to ground, the top one is to power, and the middle one is the slider. So in this case, when I connect this wire, instead of to the power supply, I decide the value of the pot, which decides the voltage across the base emitter, which then decides also which is a fraction of the power supply, and therefore decides the current that goes into the base. And so when I play with the current value, I play with the brightness of the pot, of the light bulb. So as you see here, this is set for maximum. When I go back, you will see that the light bulb starts dimming, right? All the way down to 0. And of course, when one thing you are asked to figure out why when I increase this resistance, and that means increasing the voltage going into the base, we still need a resistor. In this case, the resistor, instead of multiple K for the transistor portion of the experiment, use only 220 ohm, because multiple K is not going to be allowing these light bulbs to turn on high enough for you to see the difference. Not just for this part, but for the previous part. And so as you see here, I have produced a dimmer. And as I told you before in class, when I discussed the pot and resistors and Ohm's law or whatever, we said this is not the best way to create a dimmer, because the dimmer is such that you should pay only for the power used. But in this case, even if I use the 100-watt light bulb and I dim it to 20 watts, I still pay for 100 watts, because the other portion, the 80 watts, are still going to be dissipated by a portion of that pot. And so that is not very efficient, of course. Yes, you get the dimming, but you don't get the savings. And so the dimmers usually are a little bit more complex. They use semiconductor devices, but for the price that you have to pay, you get to save in terms of power consumption. This last part of the experiment is trying to show you that the MOSFET, in this case the IRF 510, is voltage-driven transistor. Unlike the BJT, which is current-driven, that means you need to generate the current at the base to have a current at the collector. Here, the voltage has to be high enough between the gate and the source for a current to start being generated at the drain. At this point, one of the most important things is when you see the heat sink in the back and the writing in the front, then the pins are such that you can Google them, but because the picture in the lab manual is not very clear, in this case, when you Google them, you'll find that this is the gate, the middle one is the drain, and the final one is the source. And when you want to look at the circuitry and you compare to the one of the BJT, the source is like equivalent to the emitter, the drain is equivalent to the collector, and the gate is equivalent to the base in terms of connections, right? This is an NMOS MOSFET, right? And channel MOSFET. One thing is that because it's voltage driven and because the current to the gate is always zero because of the insulation between the gate and the rest of the semiconductor material, you don't need that 220 ohm or few kilo ohm to protect the gate like we had to protect the base and minimize the current that goes into it, protect the junction, the base emitter junction. So in this case, when I connected the gate to ground, there is no current flow because VGS is not large enough and the light bulb of course is off. When I connect the wire to power, obviously I have a VGS which in this case happens to be 5 volts, and that's large enough to generate the current at the drain, which then shows through the light bulb being turned on. The part that shows that it is voltage driven is the following. Again, I turn it off, and so nothing happens. But to show that my body does not generate the current that is large enough to turn on a BJT, but because there is enough potential, and if I just connect it to my hand, to my body, then the light bulb should turn on. Unfortunately, my skin is not wet enough, right, to show because it's very dry, because it's kind of like an insulation. But if you students try it with your own hand, you will see that the light bulb will turn on. By making my fingers wet, I produced enough potential, enough voltage